Before the break, we were discussing about the size, the dimensions of the Jacobian. I said that it's 6 by n. How come it's just 6 by n? Basically, in this step, we saw that the Jacobian has two parts, one above the other. These two basically submatrices. And we saw that each one of them is basically, and these are, we can write them as vectors, Ju1, Ju2, right, Jun, right. So we have n direction vectors, one for each joint. That's why it has n columns. And how come it's 6? Basically, you remember what was these ones? These were the direction vectors, right? Because they're direction vectors in 3 dimensions. Each one of them is 3 by 1. This is a 3 by 1. This is a 3 by 1. Right? So I have n 3 by 1s, one next to each other. So this is a 3 by n, the linear part. And the same thing for the angular part. This is also a 3 by n. So if I put the one on top of the other, I will end up with a 6 by n. Right? Just adding up. Right. So to calculate the overall Jacobian, we work column by column. We can do this. We can do it separately, first for the linear Jacobian, then the angular, then put them together. Or I can calculate the whole linear and angular Jacobian for each joint. Let's say if I have them here, J omega n. Right, I could calculate these two as 1 6 by 1 vector. And we saw that we have slightly different formulation for revolute and prismatic joints. So basically I have to go to each column I calculate for each joint, which would be the direction vectors for each joint. And these direction vectors are different if it's a revolute or a prismatic joint. So I start from joint 1, 2, 3, n. I check, is it revolute? If it's revolute, I follow the top definition. If it's prismatic, I follow the bottom definition, which tells me what? The top definition will give me a 6 by 1 vector. The first 3 elements would be the linear Jacobian for that joint, which is, as we saw, the cross product of the direction of the joint, the axis of rotation of the joint, with the vector connecting the origin of the joint with the end effector origin. And for the angular part, it will be the orientation of the joint, the axis of orientation. And for if the joint is a prismatic joint, then I will have a slightly simpler form. I will have, for the linear part, it will be the axis of translation, and below it will be a vector of zeros. Again, this is 3 zeros basically. All right? Good. What is this Zi? Why did I use this notation? Right? We said that this Zi is the axis of rotation for revolute joints and the axis of translation for prismatic joints. Why do I call it Z?
Because to do the follow geometrics, you have to put the z-axis on the axis of translation or rotation.
Right. So if we follow the Denavit-Hardenberg convention, we place the z-axis at the axis of rotation for the revolute joints and the axis of translation for the prismatic joints. That's what we did last week, right? So this Zi basically relates to what? To the orientation of the z-axis of the frame located at the joint. If we follow the Denavit-Hardenberg convention, right? That's the assumption, and we should follow it. Otherwise, we have to figure out which axis to take if we put the coordinate frame randomly. But if we follow the Denavit-Hardenberg convention, we know we place the z-axis of that frame aligned with the axis of rotation. We also ensure that we put it the right way. So if it's rotating positively, which direction, right? And then we can take that z But by calculating the transformation using the Dynamic-Hartenberg from the base frame until that joint, right? If I do that, I will have the transformation matrix that represents, I don't know, let's say for joint 2 it would be something like this. I will have the transformation matrix describing the position and orientation of frame 2 with respect to the reference frame, given by this 4x4 matrix, right? Which part would be this vector Zi, which basically gives me the orientation of this vector with respect to the reference frame? Which part from this 4x4 matrix? The third column, right? We saw that this matrix represents the orientation of these three axes with respect to the reference frame. Each column is for one of the three axes. The first is for the red, the second is for the green, the third is for the blue, the Z. So if we place the Z along the axis of rotation and I calculate the forward kinematics until that joint, then I can take that Zi using this column. Whoop. Very bad drawings, but you know, don't have a mouse. All right. What is OI? What is the origin, the coordinates of the origin of frame I with respect to the reference frame? The position of the origin of the coordinate frame.
The diagonal x, y, z.
Try again. This part we saw that it shows me the orientation of these three vectors, right? So it doesn't tell me anything about where the origin is. What tells me about the origin? So it's these three, right? This is OI. Is the position of the origin, right? And if I do the forward kinematics, you know, this position will always follow, you know, we will be able to calculate for whatever orientation. That's what forward kinematics is. Calculate the position and orientation for different joint coordinates. All right. What would be O4, On plus 1? So basically I know what is Zi, right, which I needed in three places. I know what is OI. What is this On plus 1?
The position of the end effector.
The position of the end effector, so I have to do the forward kinematics until the end effector. And that's it. Right? Good. So I know everything I need to know in order to calculate the Jacobian. It's basically geometry in the end. I need to know just the forward kinematics for the end effector, but also for where each joint is. And then I can just, you know, basically create a loop where I go for each joint, I calculate where is the origin of the joint, what's the orientation of the joint, and I can calculate, you know, what's the corresponding column for that, for the Jacobian for that joint. Add them all together, and I have my Jacobian, okay? Which is what you will have to do in the lab, for the robot in the lab. You have the DH. We'll give you also this transformation matrix so you have them cleaned up, and then you will have to construct the Jacobian using these rules. All right? Let's see an example so we can get the feeling of what do we do with the Jacobian as well, right? What does it tell us? So I have this robot, two joints, planar robot, so on the plane. I'll draw it here, so we have it, and then, you know, this one. So this is Q1, this is Q2, and this is my end effector, right? And we already know how to calculate forward kinematics, so I just give you the matrices directly. So R0 to 1 would be the, let's put the frame here as well, so we have it. So this would assume that, so we have a rotation on Z, so this is X, Y, and Z. Right, so Z is coming towards you, X, Y, Z. All right, so I have the first transformation which shows me where is the first frame. So let's make the first frame as well. And Z. Zi, Z0, X0, X1, Y0, Y1. All right, so this thing rotates around this axis. Okay, and I have this transformation matrix, which is basically the rotation around Z transformation, homogeneous transformation, right? I will have the transformation till the second joint, basically this frame here, Z2, X2, Y2, and then I will have, I think that's how I took it, X3, Y3, Z3. The Zs are all coming towards you. All right, so this would be the transformation from 0 to 2 and the transformation from 0 to 3. Right. And we need to calculate the Jacobian. Basically, I have two revolute joints, so I take the revolute joint form for calculating the columns of the Jacobian. So this would be the first column, and this would be the second column. So what we have here, the orientation of the first axis of rotation, cross product with this distance, 0 to 3, right? On the linear part, on the angular part, it would be just Z1, right? For the second joint, it would be second axis of rotation, Z2, cross product with this distance, right? Vector, with this vector, not this distance. For the angular part, it will be just Z2. Right, so if I know, okay, 1 second, let's take it one by one. What would be Z1 according to these matrices you have there? 0, 0, 1. From which transformation do I take it? R01, so this would be Z1, Z1, all right, 0, 0, 1, which shows me the orientation of Z1 with respect to the reference frame. And it tells me that Z1 is basically aligned with 0, 1. Like it has 0 on X, 0 on Y, and 1 on Z, right? And it makes sense, right? Because it goes like this. What is Z2? Sorry? 0, 0, 1, but this 0, 0, 1, okay, sorry, Z2, right, which again tells me the orientation of this Z with respect to the reference frame, which is again parallel to Z0, that's why 0, 0, 1, all right, what is O1 vector? 0, 0, 0. Which 0, 0, 0? This one here. This is O1. All right, what is O2? O2 is, sorry? So this one, 0, 2, have them in the next slide, but yeah, L1, C1, L1, S1, 0. And you see these are 3 by 1 vectors, right? All of them. And what is O3? That's the last one. It is the last column from R03. All right? Good. I'm not going to write it down. So that's basically it. If I do these operations that are described there, the cross products and so on, so you can see here O3 minus O1. O1 we said it's 0, 0, 0, so this will be O3. Let's write it here, C12 plus L1 C1, sorry, L2 S12 plus L1 S1, 0. So if I do cross product 0, 0, 1, cross product this quantity here, L2 C1 2 L1 C1, L2 S1, comma 2 plus L1 S1. Basically, this will just swap the elements positions and you will add a minus somewhere. So I will end up, this is basically the first part there. Minus L1 S1 minus L2 S1 S2 L1 C1 I plus L2 C1 comma 2 and 0. Right, so if I do this cross product, you will see that these elements will basically swap and I will put a minus here. It's how cross products work. All right, and this will be basically this part here, so it will be the top left part of my Jacobian, right, these 3 elements, right? What do I have here? Here I have Z1, which is 0, 0, 1, all right, sorry. Here I will have Z2, which is again 0, 0, 1, with O3 minus O2, O3 being this minus this. I will get rid of these parts basically. So it is just L2 C1, 2 S1, 2. And again, if I cross product with this, again I will swap these 2 elements and put a minus there. So I will have this part. This is this, inverse and minus. All right, and then bottom right it will be again Z2, which is 0, 0, 1. All right. What do we see here? We see the Jacobian for this similar robot with 2 joints. 2 joints means n equals 2, so the Jacobian is 6 times 2. 6 rows, 2 columns. Right, and I can multiply it with the joint velocities to get end effector velocity. We'll see right there. Now, does the Jacobian have fixed values? So, do I have fixed numbers in all positions for the Jacobian? I added a small hint there. Are there any of these numbers changing as the robot moves? Does L1 change? Right? So what is this S1? That's sinus of Q1. Right? What is C1 is cosinus of Q1. C12 is cosinus Q1 plus Q2. Right? So these numbers change when joints move. Right? So that's why I wrote there Jacobian is a function of joint coordinates. Right? It's not, doesn't have fixed values. What does this tell me? This tells me that the end effector position, like the contribution of one joint at the end effector position, will depend on the joint coordinates. Right? So to demonstrate this, let's have a look. Let's say the robot is in this position. All right. Contribution of the velocity and the end effector due to the first joint will have, I don't know, some direction, and due to this length it will also, it affects the magnitude. Right? Let's say I change the joint configuration and now I have, I don't know, this joint configuration. Now for the same joint movement, I will obviously have different velocities here. Right here I will have much smaller linear velocities because I'm closer to the axis of rotation than in this case. Right now I have, for the same angular velocity of this joint, I will have bigger linear velocities on the end effector in this configuration than in this configuration. Right? So obviously the end effector velocity is affected by the how the configuration of the robot, the joint coordinates. That's what we say. The contribution of each joint will affect the overall end effector velocity. All right. So that's we see also in the equation in the matrix form. Jacobian is a function of joint velocities. Not all parts of the Jacobian. Sorry, the Jacobian is a function of joint positions, joint coordinates, not velocities. Right. Not all parts of the Jacobian, you see that the angular part for this robot is not affected by the joint coordinates. That's because the axis of rotation for this robot does not change when I move my joints. It's basically this robot here. If I move just these two joints, the axis of rotation for these joints don't change orientation, just change position. So the angular velocity at the end effector due to these two joints will not change. It will change if I rotate this joint as well, or this joint, because then I change the orientation of this axis. Okay, good. How do we use the Jacobian? So what can I do with this? We started saying that we use it to calculate the end effector velocities using joint velocities as input. Right? So if I know the joint velocities, I multiply them with the end effect with the Jacobian to calculate the end effector velocities. I don't have the Jacobian here, but let's take an example here. Let's say I have this Jacobian. I need to evaluate it at certain joint configuration. So let's say I take the configuration when Q1 and Q2 are 0. So I have this flat robot. Right? My robot is here. What will be the Jacobian? So if Q1 and Q2 are 0, let's write it here. When I have here 0 and 0 for Q1 and Q2. S1, S of sinus of 0, 0. Sinus of 0 plus 0, 0. So this will be a 0, right? That part will be 0 as well, correct? Right. Second row, cosinus of 0, 1, L1 plus L2, because the cosinus of 0 plus 0 will still be 1, right? And the right side will be L2. I'll have 0, 0, 0, 1, 0, 0, 1. Should have written it a bit more to the right. All right, so what happens if I multiply this Jacobian? Let's say I have I have this first joint and second joint. Let's say I have some angular velocity here. So only Q1 is moving. Let's say I have angular velocity for Q1 1 and for this one 0. What will be my end effector velocity? So if I do vector matrix with vector multiplication, Xi will be what? First element is this row with this column, will be 0. Second one, L1 plus L2, 0, 0, 0, 0, 0, last column, 1. Right. So what does this tell me? I will have 0 linear velocity on the x direction, L1 plus L2 linear velocity on y direction, 0 on z, and then 0, 0, and angular velocity around 0, around z1, right? So this tells me basically my linear velocity will be something like this, where the length of this is L1 plus L2, right? And it makes sense. If my robot is like this and I move this joint, instantaneously I will move upwards, and that will be my velocity. If I had here a minus, so basically rotating the other direction, I would have had here a minus, and my vector would have been pointing downwards, right? What happens if I have 0 velocity on the first joint and angular velocity on the second joint? Again, with the same magnitude. Will I have a bigger velocity here or a smaller velocity here? Smaller velocity, because this is a smaller radius. So let's see it here. What will I have? 0, L2, 0, 0, 0, 1. Right? You see now I have a smaller vector. It's just L2, not L2 plus L1. Right? I could evaluate this at different joint configurations. So let's say, I don't know, this one being 0, this one being 90 degrees. Right, so then evaluate the Jacobian where Q1 is 0, Q2 is 90 pi over 2, right? I would end up with different values here, but I would still be able to calculate, okay, what is the end effector velocity when Q1 is moving, when Q2 is moving, or obviously I could do this when both of them are moving, right? When whatever values I want to put here. That's how I use the Jacobian. Right? So for any joint configuration and for any input joint velocities, I can calculate the end effector velocity. Is this useful? It is, because it tells me what the end effector velocity would be. But what if I want to calculate, I have a desired end effector velocity. Let's say I want to move this end effector in a certain direction with some velocity, so slower or faster. And I want to calculate, okay, what is the joint velocities I need in order to have this resulting end effector velocity. Like that would be a little bit more useful. Like in a real scenario, an application where I don't know, I want to follow a trajectory with a certain velocity, you know, I would need basically the opposite. The end effector velocity is what is my reference, is what I want as an output, and I can say, okay, I want this velocity, say moving around the z or the y or the x, and I want to calculate what would be the necessary joint velocities for this end effector velocity. So basically, I want to calculate the inverse of this. Could I do it? And if yes, how could I do it? I'll proceed since we don't have too much time. But basically, I can take this equation that I have there and invert it. Or you had already?
You can multiply with the inverse of the Jacobian.
Yes, from the left side, right? Great. So that's the idea. We can invert this by multiplying with the inverse of the Jacobian from the left, right? And now my logic changes. Now Xi is something I know. I multiply it with this inverse of Jacobian, and I calculate Q dot, right? So this would give me the necessary velocities at the joint level in order to have an end effector velocity, the one I desire. Can I always do this? Can I always calculate this inverse of J?
No, because it's
Xi. What? This is J. Well, Xi does not affect me. Xi always is 6 by 1, right? And I'm not inverting Xi, I'm inverting J, the Jacobian. Right? You're saying that What is the condition so that I can invert the matrix?
To have determinants different.
Yes. And even more so, to calculate the determinant, it has to be square, right? Is this one square? No. Right, so I cannot do it always. What's the condition for this one to be square? This Jacobian always has 6 columns, so it needs to have 6 rows. It always has 6 rows, so it needs to have 6 columns as well. When does it have 6 columns? When I have 6 joints. Great. So in order to be able to invert this matrix and be able to control the end effector velocities, I need 6 joints. And if you remember our discussion on forward kinematics, the second lecture, we were saying that the number of joints is relating to the number of degrees of freedom. So basically this tells me in order to be able to control the end effector velocity in all 6 directions, so have 6 degrees of freedom, I need 6 joints, right? Good. So in order to calculate the inverse velocity, I need J to be square, but even not all square matrices are inversible, so it also has to have a determinant not equal to 0, or the rank has to be equal to the size of the matrix, so it has to be 6. Which tells me that even if I have a robot with 6 joints, it doesn't necessarily mean it will be 6 degrees of freedom robot, which is again something we discussed that lecture. Great. What do we need for such Jacobian? 6 joints, right? Now, there are methods to still calculate end effector velocities for robots with fewer or even more joints. Because if I have 7 joints, then again I have an issue, because I have a 6x7 Jacobian, right? But what I can do is calculate what we call the pseudo-inverse. So a matrix can have a pseudo-inverse even if it's not square, which basically has this interesting property that if we multiply it from, so we have the left and the right pseudo-inverse, so in our case we want the left one. If we multiply it from the, in this case it's the right one, If we multiply it from the right one, we end up with identity, but it doesn't work on the other side. So if I multiply it from the left, it's not going to end up with identity. And you can imagine why. Like if this is my Jacobian that has 6x2, then the pseudo-inverse, in order to give me identity, what should be its size? 2x6. So I cannot take this pseudo-inverse and multiply it from the left, because I will have a 2x6. Actually, I can do it, okay, but I will end up with a different thing. If it would still give me identity, it would be a true inverse, but yeah, it's not. But I can calculate the pseudo-inverse. The calculation, I provide it here for reference, but we don't calculate it by hand. For the lab, you have methods in NumPy to do this automatically, so you don't have to worry about it. But basically, if we can calculate the pseudo-inverse, we can use again the same idea for a reference end effector velocity to calculate the necessary joint velocities. All right. Another approach is to, before we go to another approach, basically this will give you an approximate solution. So you will end up with some joint velocities. If you multiply them from the left with the Jacobian, they will give you an almost correct end effector velocity. So it's not going to be an accurate solution. It's going to be the closest possible, right? Another approach is to basically ignore some end effector velocities. So let's say I have this robot that we saw earlier, and we saw that this is the Jacobian, the linear part. Here I think I inverted some axis, it seems. But anyway, the logic is the same. Like I have a 3x2 Jacobian here just for the linear part. what if I just ignore one of the rows, and I say, okay, I don't care about velocity on x. In this case, it's anyway 0, right? What if I just ignore that velocity and I calculate the velocities just on z and y? Right? I can do that if I want. Then I end up with a 2 by 2 Jacobian, and I can do the inverse. But this will ensure I will have the desired velocity on the two directions I have here, and we don't know what will happen on the x, on the other direction that we erased, right? It might be whatever, because we're actually not controlling it. So yeah, in this case it would be, I don't know, the Jacobian something like this, and the inverse of the Jacobian for 2 by 2 matrix we have analytical form, it's easy to calculate. It would be this one. Now, some interesting cases. What happens with this Jacobian when Q2 is 0? And the inverse of the Jacobian. What do we have here?
L2, so basically we don't
L2 is L2. Does it change?
Don't we have 1 over 0?
Where? Here?
Yeah,
Why? Because
for sine.
Q2 is 0, then sinus of 0 is 0, right? So here we have basically, we cannot calculate the determinant, which is this part, is 0, right? It's what we are saying, like, okay, it's invertible as long as the determinant is not 0. So then we don't have an inverse of the Jacobian. So even if we have, if we can end up with a square matrix and calculate the Jacobian, in some configurations, we might not be able to calculate the inverse. And we call this, I don't know if it's in this one, yeah. It's basically, they're called singularities, because they cause the Jacobian matrix to become singular, which means basically to lose rank. It's again something we discussed in the forward kinematics lecture, where we said in some configurations the robots will lose degrees of freedom, and that's what happens here. Right? We lose a rank, so basically we are less flexible in this configuration. We don't have the flexibility to control velocity in all directions. Right, so we lose a degree of freedom. Now the last thing that we'll see is a way to calculate how much freedom does the robot have in different configurations. Right, so this is something we call manipulability. So how much can we manipulate the degrees of freedom of the robot? Right, so I'm going a bit fast for this because it's mainly for reference. But basically, we can calculate, we can model the robot as an input-output system where the inputs are velocities and the joint velocities, and the outputs are end effector velocities. So if we map all the unit input velocities, basically defined like this, and we use the Jacobian equation, we end up with something like this, which ends up being basically an ellipsoid. A picture worth 1,000 words, an animation even more. Basically this ellipsoid here, in 2 dimensions it's an ellipse, and it helps us map basically the possible velocities for any configuration of the robot. So when the robot configuration is changing, we can draw at the end effector this ellipse, which shows us, what in different directions, what are the magnitudes of the end effector velocities possible. All right. So here we see this ellipse having, elongated form in this direction and a shorter form in this direction. This tells me that, okay, in this direction, I'm less flexible. I can reach lower maximum velocities for the end effector than in this direction, right? We even have cases where this ellipsoid or ellipse ends up being basically a line. I'll try to pose it. Yeah, so as we saw, when we're fully extended, we basically can only move up and down, right? No matter what velocity we put here on the joints, I will end up basically with a velocity pointing up or down, right? So this means I cannot change this velocity when I'm here. And yeah, again, this is a singular configuration, so again, I can only move in one direction and I cannot affect the velocity in the other direction. In 3 dimensions, this is a ellipsoid, which is basically an ellipse with 3 different principal components, and eventually I have 2 ellipses, one for the linear velocity and one for the angular velocity, but that's too complicated to demonstrate. Right. So that's all I had to say on the Jacobian and the velocity, and that basically completes the forward kinematics both for the positions and orientations and velocities of the end effector. Next we will talk about the inverse kinematics. And yeah, in the lab, as usual, you will practice with the Jacobian. You'll have to calculate the Jacobian for the robot on the table. Reminder, keep things simple in the lab, right? You have to use these rules that we learned, take the right things from the right matrices, multiply them, put them one next to each other, and that's it. All right, do you have any questions?